Okay. So, good evening, everyone. I am Shivani Dhok, and I welcome you all for the first tutorial session of this course, Principles of Signals and Systems. So, I will be taking tutorial every Friday around this time. Mostly, I will stick to the schedule. In case there is some change in schedule, you will be informed much prior. But yeah, this is the general time that I will be taking the tutorial session. So this is a live session that is for understanding of few people of how to solve few questions, which is generally not done in class. Like many times only concepts are given, and there are many questions which are there in your assignments for which you need some additional help. So that is what I will be doing. So this every week I will be taking questions which are related to the content of that particular week that will help you to solve your assignments. Those won't be your assignment questions, but they will just help you in building your concepts in more better way. In case you have any questions at any point of time throughout this session, you can stop me and ask. You can basically unmute yourself and ask. Please avoid using chat box because I won't be able to see the um chat box.
Excuse me, ma'am.
Yeah.
Ma'am, your voice is hearing twice, ma'am.
Sorry.
Your voice is audible twice.
Is this the issue for everyone?
No, ma'am. No, ma'am.
Yeah, okay. So please check the connectivity issues at your end, please. So if this is not an issue at everyone's place, then I just check your with your connectivity. Yeah. Okay. So I was saying that. Okay. So this tutorial you can join at your whenever you have any doubts, you can uh, unmute yourself and ask them throughout the session regarding assignment queries for that particular week. You are free to use the Q&A portal that is available on the website, and before the deadline of your assignment and after the deadline of your assignment, if you have any questions, you can post it in Q&A. I will take them up in the next tutorial session. Other than that, the notes of every tutorial session will be uploaded in a Drive folder whose link will be shared to you through NPTEL people. Other than that, this lecture is being recorded and that will be uploaded on my YouTube channel every week, mostly after 1 or 2 hours of the end of the session. The link of the playlist in which I will be uploading the lectures is posted in the chat box. I hope everyone will be able to access that. If you are not able to access, you can simply Google my name and you Google my or put my name in YouTube. You will find the channel and you can just go through those whenever you are fine to do with it. So every week's tutorial will be basically divided into two parts. First, I'll have a brief recap of whatever was covered. It will be very brief, not a detailed recap. And then I will move on to solve few questions which are related to those concepts. Any questions till now?
No, ma'am.
Okay, yeah. Okay, so let's move on with the recap of this week's content. So this week we started with very basic concepts like defining what is signal, what is system, what are types of signals and types of systems. So to begin with, we started with something known as signal. So a signal is basically a physical representation of a physical quantity, and it shows some sort of variations with respect to, let's say, space or time. Okay, so in other words, a signal is a function. You can view a signal as a function. One second. Yeah, you can view a signal as a function, and this function captures some physical phenomena. Simple examples of your signals are your voice signal. So it is change in the amplitude of your voice that happens through with respect to time. So that is your voice signal. And then we and then we looked at system, a basic introduction to system, which basically helps you to process any kind of signal, or in other words, it gives some mathematical relation or input output relation between the process that a signal goes through. For example, if you want to use an amplifier, then you have input as your audio signal and output as an amplified version of your voice. Or in other words, you have your noise cancellation earphones. Some music is going on, but then you need to and along with that there is atmospheric, like outside noise coming up. That outside noise also serves as an input to your earphones, and that needs to be cancelled out. So these things are part of signal processing, and something that processes your signal is known as system. And this course is all about understanding your signal and how systems behave and what kind of systems we have and all those things. But before that, in this particular week, we started by understanding what are different classes of signals. So the first class that we looked at was the way the domain and range of a signal look. So what happens is your signal, as I said, is a function, and a signal can be, let's say suppose it is a function of time. So here you have your amplitude, and it varies with respect to time. Now this time can be in the can so based on the nature of this amplitude and nature of this time variable, you can classify signals in different types. So the first thing that we discussed was a continuous time signal. So in continuous time signal, what we mean by continuous time signals, what we mean is this amplitude or this signal is defined for all time instances in a particular given interval. For example, if you have an interval, let's say t1 to t2, then if you take any point between this interval, you will get a particular value of that particular signal. In contrast, you have discrete time signals in which the signal will take value only at discrete instances of time. For example, let's say at 0, 1, 2, -1, and so on. So now if someone asks you what is there at this particular location, what is the value of signal at this particular location, so there is no assignment of value at that particular time instant, because the value is only assigned at discrete points, like at t equal to 0 and t equal to 1 and so on. So these are discrete times, and in nature or by nature, all the signals that we see that are naturally occurring are continuous time signals. But to process, we need to convert them to discrete time, because your computer can't handle continuous time signals. And conversion from continuous time to discrete time is done by a process called as sampling, which we will be covering towards the end of this lecture. So that is also an important part of this course. But right now, just keep in mind that continuous time signals are converted to discrete time signals by a process known as sampling. Another classification that we saw was with respect to amplitude and time together. So when you have continuous time and continuous amplitude, then these kind of signals are known as analog signals. But when you have time and amplitude both discretized, so you have discrete time and discrete amplitude, such signals are known as digital signals, and those are the signals that we generally process in our computers. But to understand how these signals behave, we first need to understand how we move from this part to this part. And for that, we first need to understand how continuous time signals are, how discrete time signals are, and so on. Okay, so this is what we have right now. Then after that, we looked at another classification in which we saw deterministic and random signals. So a deterministic signal is some signal which can be specified at every point of time. Like its output is deterministic. Like it's a yeah, it can be specified at all times. For example, a cosine wave, an exponential wave, and so exponential signal, and so on. Whereas when you have a random signal, you cannot specify it at every time instant. For example, coin toss. You don't know, it's a random variable, it's a random quantity. So at next time instant, what exactly is going to happen, you don't know. So such kind of signals are known as random signals. And random signals are very frequent and you will encounter them very frequently when you come up with communication signals and all those things. Then another classification we did was based on periodicity. So if a signal repeats after particular time duration, that is, if you have, let's say you have a continuous time signal x of t, and if you have x of t plus capital T equal to x of t for some capital T, or let's say you have an integer also, like every t duration it repeats, then such a signal is known as periodic. And when this doesn't happen, it is known as aperiodic signal. Another classification that we saw was based on symmetry. A signal is odd symmetric if, so it is an odd symmetric if you flip it, that is x of minus t is minus of x of t, and it is even symmetric when x of minus t is equal to x of t. We'll see examples of these signals in the coming questions. I'm not getting into details of that right now. Then we saw something known as energy and power signals. So a signal with finite energy is known as a energy signal. A signal with finite power is known as power signal. I'll get into the definitions of this once we have questions related to that. Yeah. After that, before going on to different kind of systems, we looked at some special kind of signals. The first one was unit step. So when you have a continuous time unit step, so that is given a special symbol, that is u of t, which is equal to, it is 1 when t is greater than or equal to 0, and it is 0 otherwise. Another signal that we saw was unit impulse. For that, we defined a signal, an intermediate signal, which is delta epsilon of t, which is equal to 1 by epsilon when t is in a range of minus epsilon by 2 to epsilon by 2, and it is 0 otherwise. And the unit impulse function, that is delta t, is given by limit this epsilon tending to 0 delta epsilon of t. So this is your unit impulse signal. And then we saw different properties of this unit impulse signal. The first property that we saw was, if you have any signal x of t, and if you multiply it by an impulse which is shifted at some t naught, then this gives us x of t naught delta t minus tau d tau. The second property that it has is delta of a is equal to a delta. And the third property is the shifting property. So if you have x of tau from minus infinity to infinity, delta t minus tau d tau, this is nothing but your x of t. So this is your shifting property of unit impulse. And the counterparts for discrete time signals, So discrete time unit step. So it is u of n. It is equal to 1 when n is equal to 0 and it is 0 otherwise. And unit impulse. You have delta n, which is equal to 1 when n equal to 0. It is 0 when n is not equal to 0 or everywhere else. Other than that, we looked at different kinds of signals, in which the first one was complex exponential. We looked at complex exponential. I will just note them down. I'll take a few examples related to that. Then we also looked at generalized complex exponential. Then we looked at exponential signals. Sinusoids. Yeah. So these are the other few things that we looked at, and yeah. And once after that, we moved on to see what are systems or some classifications of systems. So two classifications of systems we looked at. The first one was memoryless. So memoryless system is a system whose input at current time instant depends on depends on the the output. Let me write it down. So a system is memoryless if its output at current time instant depends on the input only at the current time instant. So if the current output depends on only the current value of input, it shouldn't depend on the past values of inputs or future input values. It should only depend on the correct current value of inputs. Such systems are known as memoryless systems. And another class of systems that we looked at was causal. So for this, the current output depends on current or past values of inputs. But there is no future dependence. And here there is no future for memoryless, no future, and this and is important, and past dependence. So this was all that was covered in this particular week. If you have any questions till this point, please let me know. Otherwise, I'll move on to the questions that I have planned to cover today.
No questions, ma'am. You can proceed.
Yeah, yeah. Okay. Let's move on to the first question that I have planned to cover today. So the first question here says that classify the following signals as even and odd signals. So the first signal that is given to us is x of t, which is equal to u of t plus 2 minus u of t minus 2. And just again a recap, what are even signals? A signal is even when x of minus t is equal to x of t, and a signal is odd when x of minus t is equal to minus of x of t. Okay, so the signal now given to us is x of t equal to u of t plus 2 minus u of t minus 2. So how does this signal look? That is the first question. Because just by substituting it as x of minus t and trying to simplify it mathematically, it becomes a little bit tedious. So what we can do is, instead of doing that, we can start by visually representing this signal or plotting this signal. So this signal depends on which signal? It basically depends on a unit step signal. So this u of t is your unit step signal. And how does your unit step signal look? It looks something like this. So it is 1 when t is greater than 0, and it is 0. So it looks something like this. This is your unit step signal. This is u of t, this is t. Okay. Now how do we define unit step signal? Unit step signal u of t is 1 for t greater than or equal to 0 and 0 otherwise. So then in that case, how will your signal u of t plus 2 look? So your signal u of t plus 2 will be equal to 1 when the argument is greater than or equal to 0. That is, t plus 2 is greater than or equal to 0 or 0 otherwise. Or in other words, t is greater than or equal to minus 2. So this signal looks like this. So this is your 2, sorry, yeah. This is your minus 2, and it is equal to 1 from minus 2 and so on. It is equal to 0 otherwise. So this is your signal u of t plus 2 as a function of t. Okay, so this is the first part. We know how this particular signal look like. Now the second thing that we need to look at is how u of t minus 2 look. So this will be equal to 1 when its argument is greater than or equal to 0. That is, t minus 2 is greater than or equal to 0, or in other words, t is greater than or equal to 2 and it is equal to 0 otherwise. So now how will this signal look? So it will start from 2. It is 1 for 2 greater than or equal t greater than or equal to 2, and it is 0 otherwise. So this is u of t minus 2. Okay, so now we know u of t plus 2. We know u of t minus 2. What we need to construct is x of t, which is u of t plus 2 minus u of t minus 2. So let us do that. So what do we have? Okay, so the first signal that we had was something like this. So this is u of t plus 2. Then we had something like this. This is 1, this is also 1. U of t minus 2. Now you want x of t, which is u of t plus 2 minus u of t minus 2. That is, you need to subtract this particular signal from this particular signal pointwise. Like for every value of t, you need to subtract this signal from this signal. For example, if you consider this particular point, then for t equal to minus 2, your u of t plus 2 is 1, but your u of t minus 2 is 0. So till for this particular value, like t equal to minus 2, your x of t will be equal to 1. And this will go on till this point, for which your u of t minus 2 is 0 and u of t plus 2 is t plus 2 is 1. So from minus 2 to 2, your x of t will be equal to 1. And when you have t less than minus 2, like in this region, both of the signals are 0. Similarly, when you have t greater than plus 2, sorry, this is plus 2. Yeah. When you have t greater than 2 in this particular region, both of the signals are having value 1, so its subtraction will be equal to 0. So for t greater than 2 and for t less than minus 2, the signal value is 0. So this is how your x of t look. Okay, now by just looking at this particular signal, can you tell if it is an odd signal or an even signal? You need to look at this particular definition. X of minus t equal to x of t. Okay. So, sorry. Yeah. This signal is your x of t. Now from this you want to get x of minus t. So what happens? Whatever, so now your t1 is minus t. So whatever was there at t will now be available at minus t. So basically you are now flipping your signal along this direction, like along this vertical axis. So whatever was at 2 will now be available at minus 2. Whatever was at minus 2 will be available at minus 2. Whatever was there at minus k will be there at k. So when you do that, your x of minus t will now be again like this. So the value which was at minus 2 is now at 2, and whatever was at 2 is now at minus 2. Is that clear?
Yes, ma'am.
Yeah. So what does that mean? By visually, x of minus t is equal to x of t, which means that this particular signal is even signal. Any questions till this point? At any particular step, like constructing the signal, plotting, flipping the signal, at any point of time, any questions? Because this is the very basic thing in signals and systems. If you don't understand this, it will be very difficult to move ahead.
Ma'am, I have a different.
Yeah.
Ma'am, after constructing x of t plus 2 and u of t plus 2 and u of t minus 2,
Huh?
how did you construct x of t, like u of t plus 2 minus u of t minus 2?
Huh. So this is okay. So x of t is what? U of t plus 2 minus u of t minus 2, right?
Oh,
So it's like you're subtracting u of t minus 2 from u of t plus 2 signal for
okay, ma'am.
each and every value of t. So this is your x-axis, right? So this changes for t. So for example, when your t is somewhere here, you need to subtract this value of u of t plus 2 with this value of u of t minus 2. So which is 0, like this. So
Okay.
this value, point by point you subtract.
Okay.
So u of t plus 2 at, let's say, some t naught, if it is 1, and u of t minus 2 at that particular t naught, if it is 0, then 1 minus 0 is 1. Like that you go on doing for every value of t. That makes sense?
Yes, ma'am. Yes, ma'am.
Yeah. Any other questions? Okay.
No, ma'am.
If not, yeah, okay. If not, then let's build upon this particular question again more. Now you are given. Now let's move on to the second part. So in the second part, the signal given to you is x of t equal to t times u of t plus 2 minus u of t minus 2. So this is our good old signal. This is from part 1. We know how it looks. And this is something new. So you can write this as x1 of t into x2 of t, where your x1 of t, your x1 of t is t, and your x2 of t is u of t plus 2 minus u of t minus 2. The signal you have seen in the previous question. And how does your x1 of t equal to t look like? It's a straight line with slope 1. So you have your x1 of t, which is equal to t for all t. So this is a straight line with slope 1. And your x2 of t, this is from minus 2 to 2, and that is equal to 1. And for all other values, it is equal to 0. Something like this. And your x of t is basically product of these two. Okay, so when you multiply these two signals, you get your x of t. And what do you mean by multiply? Point by point multiply. Like x, for each and every value of t, you multiply the values, corresponding amplitude values. For example, okay, to do that, okay, yeah. For example, if you have, let's say, some t naught here, then you take up this value of x2 of t and you take up this value of x1 of t and multiply it. That will give you the corresponding value of x of t. This is your point by point multiplication. This is the same way we did the subtraction of signals in the previous part. Same way, no change. Only now you are doing multiplication. Okay, so to do that, let us see. Let us just look at x2 of t first. So this x2 of t is 0 from minus 2 to from minus infinity to minus 2. It is 0 from 2 to infinity. So for all values of t which are less than minus 2, and for all values of t that are greater than 2, your x2 of t is 0. So anything multiplied by 0 will be equal to 0. Therefore this x of t for t less than minus 2 and t greater than minus 2 will be equal to 0. So when you have here minus 2 and you have plus 2, so this x of t for t greater than 2 and for t less than minus 2, that is equal to 0. And this x2 of t, this x2 of t, when you have t lying in this region, so in this region, that is from minus 2 to 2, this region, your x2 of t is equal to 1. So anything multiplied by 1 will give you the same thing. So in this region, this x2 of t is equal to 1. So it will preserve the value of x1 of t, which is equal to t. So this signal from -2 to 2 is equal to t. Since x2 of t equal to t, at t equal to -2, it will take a value of -2. And at t equal to 2, it will take a value of 2. So this is how your signal look like. This is your x of t. Is this clear? Any questions till this point?
Ma'am,
Yeah,
ma'am, why did you take T naught there?
just to explain. I
Okay.
was just saying that you have x of t naught here. You have x1 of t naught, you have x2 of t naught, then x of t naught will be equal to x1 of t naught into x2 of t naught. It
Okay,
was
ma'am.
just for explanation. Yeah. For yeah. Okay. Now we need to figure out whether this particular signal is even or odd. So to do that, we need to understand how does your x of minus t look. So what do you mean by x of minus t? You need to create a mirror image. Mirror image with respect to your vertical axis. Like you need to flip it. So whatever was there at 2 will now be available at minus 2. So you have minus 2 here, you have 2 here. So whatever was there at 2 will now be available at minus 2. So you have 2 here. So this particular point will go here. And similarly, you have minus 2 here. This particular point will go here. So you will have a signal which is something like this. Yeah, let me move it a bit. Yeah. So this is your x of minus t. So obviously your x of t is not equal to your x of minus t. Which means this is not an even signal. But is it odd? So for that, you need to figure out what is x minus of x of t. So now you need to get minus of x of t. What do you mean by minus of x of t? You just need to flip it about the horizontal axis. So for if at t equal to 2, your value of x of t was 2, now it will go down and it will become minus 2. So you need to flip the signal about your horizontal axis like this. So what you will see is something like this. So at t equal to 2, your x of t was 2. So now it will be at minus 2. And for t equal to minus 2, it was minus 2. So it will become 2. So this is your x of t. Now if you compare your x of minus, sorry, this is minus of x of t. Yeah. Now if you compare your minus of x of t and x of minus t, both are same. So from these two, what you can see is your x of t, x of minus t is equal to minus of x of t, which means that this is an odd signal. Is it clear? Any questions?
No, ma'am.
Okay. If not, then let me move on to the last part of this question. So this question is, you have x of t, which is equal to u of t minus u of t minus 2. So again, you have your u of t. We have seen this earlier. U of t looks something like this. 1 second. Yeah. So u of t is equal to 1 for t greater than 0 and 0 otherwise. And u of t minus 2, we had seen it starts from t minus 2 greater than 0, that is t greater than or equal to 0. So 2, and it is 0 otherwise. And now your x of t is u of t minus u of t minus 2. So again, when you do point by point subtraction, only in this region your u of t minus u of t minus 2 is equal to 1. Otherwise, both of them have same values and hence it will be equal to 0. So what you get is a small pulse like this from 0 to 2. Okay. Then what will be x of minus t? So x of minus t will be basically, you need to flip it. So whatever was there at minus 1 will, whatever was there at 1 will now be available at minus 1. Whatever was there at 2 will now be available at minus 2. So this entire thing will be, you just need to take a mirror image of this in this side. So you will get something like this. So from minus 2 to 0, it will be non-zero, and it will be equal to 1 and 0 otherwise. So again, your x of t is not equal to x of minus t, which means that it is not an even signal. Now let us check whether it is odd. So for odd, we need to construct minus of x of t, which means we need to flip this x of t about the horizontal axis. That is, take a mirror image with respect to this horizontal axis. So you will get something like this. From 0 to 2, it will be non-zero, but now earlier it was at 1. For x of t, it was at 1. Now it will be at minus 1. So this is your minus of x of t. Now if you compare your x of minus t and minus of x of t, those both are not same. So x of minus t is not equal to minus of x of t, which means that this is not an odd signal. So this particular signal is neither an even signal nor an odd signal. So these kind of signals exist. Any questions till this point?
No, ma'am.
Okay, so before going on to the next question, one side note I will like to give you all is, any signal x of t can be written as a summation of its even and odd component, such that x of t is equal to xe of t plus xo of t, where xe of t is x of t plus x of minus t whole divided by 2, and this is an even signal. And xo of t is equal to x of t minus x of minus t whole divided by 2. This is an odd signal. This is a standard thing. Now a quick try you can do at your place is try to represent this particular signal in question one's third part as a decomposition of even and odd signal. Like construct xc of t and xo of t for this signal ut minus u of t minus 2. So this is an interesting thing to note, and this property might be useful in subsequent lectures. Okay, so let me move on to the next question. So this question is related to your unit impulse, and we
Excuse
had
me, ma'am.
defined. Yeah,
Ma'am, previous slide 1 minute, please, ma'am. I'll just make a note
don't
of it.
don't worry. I'll share these notes. These will be shared to you. Even if you miss, don't worry. Let me
Okay,
know once you're.
fine.
Yeah. Okay. Yeah. Okay. So now let's move on to the next question. So the first question here is, what is the area under unit impulse? So this is a standard property. We had seen that in the class also, but let me just revisit that. So your unit impulse is defined as limit epsilon tend to 0 delta epsilon of t, where this delta epsilon of t is something like this. It ranges from minus epsilon by 2 to epsilon by 2, and it is equal to, or its height is equal to 1 by epsilon. We write it here. Okay, so the area under this delta epsilon t will be integral minus epsilon by 2 to epsilon by 2, 1 by epsilon dt, which is equal to 1 by epsilon can come outside t, and then you have epsilon by 2 minus of minus epsilon by 2, which comes out to be equal to 1. So area under this intermediate function delta epsilon t is equal to 1. Now area under unit impulse you can write as integral limit from minus infinity to infinity, epsilon tends to 0 delta epsilon of t. Okay, dt. And in this particular integration, this is not in general, you can pull out limit outside. I don't want to get into details of that.
Okay.
Delta epsilon of t dt, which comes out to be equal to 1. Okay, so area under this unit impulse is also equal to 1. This is a standard property. This is unit area, and that's why it is known as a unit impulse. Okay, any questions?
No, ma'am.
Yeah. Okay, yeah, sorry. Yeah, okay. So if there are no questions, then let me move on to the next question. So now the question is, we need to find the value of integral a to b e power minus t delta 5t minus 10 dt for different combinations of a and b. So before doing that, we'll start with this general equation, integral a to b e power minus t delta 5t minus 10 dt. We'll try to simplify this particular thing first. Okay, so this we can write as integral a to b e power minus t delta 5, I can take common, t minus 2 dt. Okay, after that I can use this property that using delta a t equal to 1 upon mod a delta t, I will get this particular left hand side equation now reduces to, so we have, let me write it as I, or let's say it's a function of I of AB. So this I of AB I can write as integral a to b e power minus t, this 5, that is 1 by magnitude of 5 is again 5 delta t minus 2 dt. So this is nothing but integral, okay, yeah. Yeah, 1 by 5 integral a to b e power minus t delta t minus 2 dt. Okay, so now we have this integral here. Now we'll use other property of the impulse, unit impulse, that is using this property, some function f of t into delta t minus t naught will give me f of t naught into delta t minus t naught. Okay, for all t naught, and for our case f of t is e power minus t and t naught is equal to 2. So therefore I of AB now becomes 1 over 5 integral a to b e power minus f of t naught, that is e power minus 2 delta t minus 2 dt, which is equal to 1 by 5 integral a to b, this I can take out, e power minus 2 delta t minus 2 dt. Okay, now we need to evaluate this particular integral for different values of a and b. So the first combination given to us is a equal to 3 and b equal to 6. So the first combination is a equal to 3 and b equal to 6. So we have seen that area under this unit impulse is equal to 1 when these limits are a minus infinity to infinity. So that we had already seen. But when you have different limits, how does it look? Okay, so you have this unit impulse which is located at 2, like this. Okay, so this is the unit impulse. This is basically your delta t minus 2. And we know that its integral for the entire time range is equal to 1, that we have seen by the property in the previous part of this question. Along with that, suppose instead of from minus infinity to infinity, I take this range. Then also the area under this particular curve will be equal to 1. As long as this particular point 2 is included in the range of integration, the area under the curve will be equal to 1. If this 2 or if this impulse is not in the region of integration, for example, the region of integration is, let's say, this impulse is not located. The signal is 0 throughout the range of integration. So in that particular range, the integration value will be equal to 0. So when your a equal to 3, your a is equal to 3 and your b is somewhere equal to 6. So this is your region of integration. And your impulse is not included in this region. So therefore your integral value a comma b for a equal to 3 and b equal to 6 comes out to be equal to 0. Is it clear? Any questions till this point?
No.
Okay, let's move on to the second part. Now your A is equal to -3 and B is equal to 1. So again, you have your unit impulse, which is located at 2, and your region of integration is from -3 to -1. So this is your region of integration. So again, your unit impulse, or delta t minus 2, is outside the region of integration. Which means that integral -3 to 1 delta t minus 2 is equal to 0. So therefore, I of -3 comma 1, which is equal to e power minus 2 by 5 integral -3 to 1 delta t minus 2 dt is equal to 0. Now in the third part, we have a equal to -3 and b equal to 3. Now you have your impulse at 2. This is, let's say, 0. This is 3. This is -3. And this is the region of your integration. Your impulse lies here. Now your impulse is included in the region of integration. Delta t minus 2 is in the region of integration. So therefore, your I of -3 comma 3, which is equal to e power minus 2 by 5 integral -3 to 3 delta t minus 2 dt. This integral is now equal to 1. So your integral value finally comes out to be equal to e power minus 2 by 5. And similarly, when your a is equal to minus infinity and b equal to minus infinity, that is I of minus infinity to infinity, which is nothing but e power minus 2 by 5 integral minus infinity to infinity delta t minus 2 dt. We know that by definition of unit impulse, this thing is equal to 1. So therefore, this comes out to be equal to e power minus 2 by 5. Is it clear? So a simple note, if you have some integral I1 of a comma b, which is a to b delta t minus t naught dt, this is equal to 1 if t naught lies between a and b, and it is 0 otherwise. Is it clear? Any questions? Okay, if not, then let me move on to the next question. So now let us move on to the periodic signals. So the question here says that, is the signal x of t equal to cos 0.2 t periodic? If yes, find the fundamental period of this particular signal. So what do you mean by periodic signal? So signal x of t is periodic if x of t plus capital T is equal to x of t for some t, for some capital T, and this should happen for all small values of t. So for all t, then the signal is known as a periodic signal. Okay, this is true. And the smallest value of t, the smallest value of capital T, for which the equation 1 holds, is known as the fundamental period. Okay, so now we need to figure out whether the given signal x of t is periodic or not. So x of t is given to us as cos of 0.2 t, which is equal to cos of 0. Okay, yeah, this is given to us. So now let us evaluate x of t plus capital T, which is equal to cos of 0.2 little t plus capital T, which is equal to cos of 0.2 t plus 0.2 capital T. Now we know that cos of theta plus 2 pi is equal to 2 pi is equal to cos of theta, or for that matter any integer multiple of 2 pi. This equation holds. So therefore this will be equal to x of t if your 0.2 t is equal to some integer multiple of 2 pi. Okay, so therefore your 0.2 t should be equal to k2 pi, which means that t should be equal to k2 pi by 0.2, which comes out to be equal to k times 10 pi, and this k is integer value, so this k can be from 1, 2 and so on. So the smallest value of k for which this holds is 1. So the smallest value is 1. So therefore the fundamental period is 10 pi. So this particular signal x of t equal to cos of 0.2 t. So x of t is periodic with fundamental period ten pi. Any questions? So how does this signal look? This is a cosine signal. This is t, x of t starts from 1 and goes minus 1, 1 and like this and so on. So this is your one period. So this particular distance is 10 pi. And if you just go on, so this particular distance throughout will be basically 20 pi and so on. So this is the signal that you have. So this continues in both the directions. So after this after this 10 pi, your signal again starts repeating. Similarly, after this, your again signal starts to repeat and so on. Any questions? Okay, if not, then let me move on to the next question. Now we have a similar question, but instead of continuous time, now we have a discrete time signal. Okay, so the question given to us is the signal xn equal to cos of 0.2 n periodic? If yes, find the fundamental period. So for discrete time signal, x of n, periodicity means that your x of n plus capital N should be equal to x of n for all n, and n belongs to the set of integers. So this is so this is basically your set of integers. So your capital N should be an integer value. If this happens, then that particular signal is periodic, otherwise it is not. Okay, So the signal given to us is x of n equal to cos of 0.2 n. Yeah, before that, the smallest value of n for which this holds will be its fundamental period. Same definition. So x of n is given to us as cos of 0.2 n. So x of n plus capital N will be equal to cos of 0.2 n plus capital N, which is equal to cos of 0.2 n plus 0.2 capital N. Again, if we repeat the same story that we had here, like cos of theta plus 2 in the plus integer multiple of 2 pi will give me the same cos value. So this will be equal to x of n if 0.2 n is some integer multiple of k2 pi. So therefore, your n should be equal to k2 pi by 0.2, that is k times 10 pi, and smallest value will be equal to 10 pi. Now, this particular value is not an integer. Since this is not an integer, your x of n is not periodic or aperiodic. There was another test that was done in class. So this x of n can be written as cos of 2 pi fn. So your 2 pi fn is equal to 0.2. Your 2 pi f is equal to 0.2, which means that your f comes out to be equal to 0.2 by 2 pi, that is equal to 1 over 10 pi. So if this particular thing is rational, then the signal is periodic. If it is irrational, then this signal is not periodic. So this is an irrational number, which means that your x of n is aperiodic. Is it clear? Any questions?
No, ma'am.
Okay. Anyone else? Any questions?
Sorry, ma'am. Excuse me, ma'am.
Yeah.
Ma'am, here in the question, x of n is cos of 0.2 n. If another
Huh?
signal is added to that, then how can we find the periodicity, ma'am?
Sorry, I didn't understand your question.
Actually, x of n is a single signal, ma'am. That is cos one term is there. Two more
Huh?
terms are added to that. Then how can we determine the periodicity of the signal, ma'am? For example, cos of 0.2 n plus sine of 0.4 n, likewise, if it is given, then how to find the period of signal, ma'am? Fundamental period.
Okay, so what happens is, okay, 1 second. Let me add a page. So your question is, you have x of n, which is equal to, let's say, cos of an. Let's take something, cos of pi an plus cos of pi bn, something like this. Okay,
Okay,
you
ma'am.
have, or let's be more specific. Let's be cos pi n plus cos of 0.2 pi n. Okay, something like this you are given, and you want to figure out whether this particular signal is periodic or not, right?
Yes, ma'am. Yes, ma'am.
And you want to determine its fundamental period. So first you can check its periodicity by the definition. Okay, so x of n plus capital N, that you can do. So this will be equal to pi n plus capital N plus cos of 0.2 pi n plus capital N. Okay, so this will be equal to cos of pi n plus pi n plus cos of 0.2 pi n plus 0.2 pi capital N, right? Now, this particular thing will be equal to cos of pi n when your pi capital N is some integer multiple k1 of 2 pi, right? So your n should be equal to k2 pi by pi, or rather 2k1, right? Till this point it is correct. Now you take up your second term. The second term will be equal to your cos of 0.2 pi n if your 0.2 pi n is equal to some k2 multiple of 2 pi. So your n will be equal to 2k2 by 0.2, that is equal to your 10k2. Okay, now you need to find smallest values of k1 and k2 such that you get same value of n. Okay, now this n is greater, like this 10 times k2. If you set k2 equal to 1 here, or rather what you want to do is you want this n and this n to be equal to be same, or in other words you want 2k1 equal to 10 times k2, or you want k1 equal to 5 times k2, right? And this k1 and k2 should be integers. So now you need to find out the smallest value of k1 and k2 that satisfies this particular equation that we have gotten here. So now if you have k2 equal to 1, then in that case your k1 turns out to be equal to 10, and your n, which is equal to 2 times k1, which is equal to 10 times k2, is 10. So your signal is periodic with period 10. Does that make sense? Is it clear? Any questions?
Yes, ma'am. I have a question.
Yeah.
So it is necessary for discrete. So it is necessary to for a discrete periodic signal that n have to multiple of pi.
Yes.
Okay, ma'am.
So okay, so now what is necessary is you can write your cosine signal in this form, right? So this f should be a rational number. That's all. And this periodicity, when you are defining your x of n plus capital N, this capital N should be an integer. It can't be a rational number or irrational, nothing. It should be an integer. That's all. And this actually translates to this particular definition. Does it answer your question, Ajay?
Yes, ma'am. Yes, ma'am. Okay.
Yeah, okay. Yeah. Okay. If there are no further questions, then let me move on to the next question. So the next question is related to periodicity of complex exponentials and standard real exponentials. So what I'll do, I'll try to solve this question in parallel, like not parallel, but I'll just divide the page into two parts. So the question here says that are the signals x1 of t, which is equal to e power minus 2 pi t. So this x1 of t is basically your real exponential, and x2 of t, which is e power minus complex exponential, are these periodic? And if they are periodic, then what is the fundamental period? So let us start with real exponential. And the signal given to us is x1 of t equal to e power minus 2 pi t. So let's start with x of t plus capital T, which is e power minus 2 pi t plus capital T, which is equal to e power minus 2 pi t into e power minus 2 pi t. Now in order to have this equal to e power minus 2 pi t, this thing should be equal to 1. and this will happen only when your capital T equal to 0, which means that your signal is not repeating at all. Only at capital T equal to 0 this is going to happen. Otherwise it is not going to happen, which means that such a signal, a real exponential, is not periodic or it is aperiodic. Now let us move on to your complex exponential. So you have your x of t as e power minus j 2 pi t. So then your x, so this was x1 of t, this is x2 of t. So x2 of t plus capital T, it is equal to e power minus j 2 pi t plus capital T, which is equal to e power minus j 2 pi t into e power minus j 2 pi capital T. Now in order to have this equal to x2 of t, your x of, or this particular thing, should be equal to 1. Now how does this complex exponential look? E power minus j 2 pi capital T is equal to cos of 2 pi t plus j times sine of 2 pi t. So in other words, this particular thing should be integer multiple of 2 pi, and in that situation the sinusoid term will be equal to 0. If this happens, this term will be equal to 0 and your cosine term will be equal to 1. So in that situation your t will be equal to k, and the smallest value of k is t equal to 1. Okay, so therefore this complex exponential, it is periodic with period t equal to 1. Is it clear? Any questions? Any questions? Your real exponentials are not periodic, but your complex exponentials are periodic. Real complex exponential, sorry, continuous time um, complex exponentials. Any questions? Okay, if not, then let me move on to the next question. So now the next question is related to again a complex exponential, but it is not a continuous time complex exponential, but it is a discrete time complex exponential. Any questions? Okay. So let us try to understand. Let us try to apply the definition of periodic discrete time signals. So x of n plus capital N, it is equal to e power j to n plus capital N. This comes out to be equal to e power j to n into e power j to capital N. Now this thing needs to be equal to 1. Again, we can go back to the definition of this complex exponential, that is cos of 2n plus j times sine of 2n. Now for this cosine term to be equal to 1, for this term to be equal to 1 and this term to be equal to 0 simultaneously, your 2n should be equal to some integer multiple of 2 pi. which means that n should be equal to some integer multiple of pi by n, and smallest will be pi by n. Now again, pi is is an irrational number. Pi by sorry pi k pi sorry, yeah, n should be equal to pi. Now this pi is an irrational number, and this is not an integer. So your n cannot be an integer in this particular setup. And if n cannot be an integer, your e power j2n is, so this particular signal, or rather your x of n, is aperiodic. Is it clear? Any questions? So in continuous time signals, your cosines or your sinusoids and your complex exponentials are always going to be periodic. But when you go to your discrete time signals, it is not the case. For very specific cases, it is going to be periodic. As long as you get your number, the period or this capital N as an integer value, you are guaranteed to get some periodicity. Otherwise, they can't be periodic. So you can't say that a discrete time sinusoid or a discrete time complex exponential is always going to be a periodic signal. So you have to be very careful and critically look at that particular signal to say whether it is going to be a periodic signal or an aperiodic signal. Is that clear? Any questions? Yeah. Okay, if not, then let me move on to the um, to the next question. Okay. So next question says that find the energy of the electrical signal 50 hertz 220 volt RMS. Okay. So you have xt. So this, how does this signal xt uh, look like? Your x of t is amplitude, and that amplitude is a peak to peak value. It's your peak value. So that is basically your 220 root 2, and let's say cos of 50 hertz, so 2 pi f, that is 50 t. So this is basically 220 root 2 cos of 100 pi t. You can take sine also, it will give you same results. So the first thing that you need to find out is in this question is the energy of the signal. So while doing the recap of this week's content, I discussed about one particular classification of the signal that is based on energy and power. So energy of a signal is so energy of a signal, okay, so if a signal has finite energy, then that particular signal is known as energy signal, and if a signal has finite power, then that particular signal is known as a power signal. Okay, so you have, so how do you define energy? So energy is defined as integral minus infinity to infinity magnitude of x of t square dt. So this is equal to, for our case, minus infinity to infinity 220 root 2 cos of 100 pi t whole square dt, which is equal to 220 root 2 whole square integral minus infinity to infinity cos square 100 pi t dt. Cos square you can write as 1 plus cos 2 theta by 2. So this comes out to be equal to 220 root 2 whole square by 2 integral minus infinity to infinity 1 plus cos of 200 pi t dt. So this comes out to be equal to 220 root 2 whole square by 2 t plus sine of 200 pi t by 200 pi minus infinity to infinity. So just by looking at the first term only, you can say that this goes to infinity. So therefore, the energy of this signal goes to infinity, which means that this is not an energy signal. Okay.
Degree in the chari.
Sorry.
Degree. Varatelia.
Request to all the participants, whenever you don't have a question, please mute your microphone. And whenever you have questions, then freely unmute yourself. But whenever you don't have, please keep it on mute. It will help others. Okay. So now when the signal is not an energy signal, the next question that comes into our mind is it a power signal? So for that, let us compute the power of this particular signal. And what do you mean by power? So by definition, power is limit t tending to infinity 1 by t integral minus t by 2 to t by 2 magnitude of x of t whole square dt. Okay, so therefore this p for our case is limit t tending to infinity 1 over t integral minus t by 2 to t by 2. You have 220 root 2 whole square into cos square 100 pi t dt. So you can take out things common. So you have limit t tending to infinity 1 by t. You can take 220 root 2 whole square outside minus t by 2 to t by 2. Cos square you can write as 1 plus cos 200 pi t by 2 dt. And this comes out to be equal to limit t tending to infinity 220 root 2 whole square by t. You have t plus, you can put 2 here, sine 200 by t from minus t by 2 to t by 2. So this is equal to limit t tending to infinity 220 root 2 whole square by 2 capital T. The first term is t by 2 minus of minus t by 2 plus sine of 200 pi capital T by 2 minus of sine of minus 200 pi t by 2. So this comes out to be equal to limit capital T tending to infinity 220 root 2 whole square by 2t. This is t plus 2 times sine of 100 pi t. So this t gets cancelled. You have 1 here and this t comes here. So as t tends to infinity, this term goes to 0, and what survives is the first term, that is your constant term. So that comes out to be equal to 220 root 2 whole square by 2. Okay, so this is less than infinity, this is finite. So since the power is finite, x of t is a power signal. Any questions? Okay, if there are no questions, then let me move on to the next question. So the next question says that classify the following signal as an energy or power signal. Yeah, okay. Just a moment. Yeah, so the first signal given to us is x of t equal to max of 0 and t. So you have this thing here. Yeah, let's say this x-axis is your t, and you have x of t here, and your signal is x of max of 0 and t. So when we move from minus infinity till 0, the max your t value is negative. So for t less than 0, your x of t will be equal to 0. So in this region, your x of t equal to 0. The max value of a negative and a 0 is 0. And when you have t greater than or equal to 0, your max of 0 and t will be equal to t. So in other words, you can write this signal as equal to t for t greater than or equal to 0, and it is 0 otherwise. Okay. So now you need to compute energy and power of this particular signal. So how does your energy look? Your energy is integral minus infinity to infinity magnitude of x of t square dt. Now integral your x of t is equal to 0 from minus infinity to 0, right? So therefore what you get here, and only from 0 to infinity your x of t is equal to t. So you have t square dt. So this comes out to be equal to t cube by 3 from 0 to infinity, which tends to infinity. So therefore this is not an energy signal. So energy tends to infinity. Similarly, we can compute its power. Just a minute. One second. Yeah, so power is given by 1 by capital T integral, again 0 to infinity, minus t by 2 to t by 2 magnitude of x of t square dt. So this is equal to 1 and there is a limit outside, sorry. Limit t tending to infinity, limit t tending to infinity, integral, again it is now 0 for negative values of little t. So 0 to infinity, 0 to t by 2 t square dt. This comes out to be equal to this thing. Let me add a page, I don't want to cram things here. Yeah, this is equal to limit t tending to infinity 1 by t little t cube by 3 from 0 to t by 2. This is equal to limit t tending to infinity 1 by t capital T cube by 24 square. So again, as t tends to infinity, t square also tends to infinity. So this also tends to infinity. So what we see is your energy tends to infinity. Your power also tends to infinity. Since both of these are not finite, this particular signal is neither a power signal nor an energy signal. So this is neither an energy nor a power signal. Is it clear? Any questions? Okay, if not, then let me move on to the second part of this question. So the second part of this question is, this is equal to, so your x of t is equal to e power minus j t plus 4. Okay, now your magnitude of x of t is magnitude of e power minus j t plus 4. Now this is a complex exponential. And what does a complex, yeah, this is a complex exponential, and complex exponentials are unit magnitude. So this is equal to 1. So magnitude of x of t is equal to 1 for all values of t. Okay, so now the energy of this signal is integral minus infinity to infinity magnitude of x of t square dt, which is integral minus infinity to infinity 1 dt, and we know that this will tend to infinity. So energy is not finite. So this is definitely not an energy signal. Now let us take a look at power. So your power is limit capital T tends to infinity 1 by t integral minus capital T by 2 to t by 2 magnitude of x of t square dt, which is equal to limit capital T tends to infinity 1 by t integral minus t by 2 to t by 2 1 dt. So this is equal to limit capital T tends to infinity 1 by t little t from minus t by 2 to t by 2, which is equal to limit t tends to infinity 1 by t into t, which is equal to 1. Now this power is finite. So what we see here is your energy tends to infinity, but your power is equal to 1, which is finite. So this is finite. So this means that this signal x of t is an or is a power signal. Is it clear? Any questions? Okay, if not, then let me move on to the last part, last question of today's tutorial. And this is based on systems. I have taken only one question on systems because in this particular week, systems was just introduced. It was not done in detail. Only two classifications of the system were introduced. One was based on memory and one was based on causality. And I had discussed these two when I was doing a quick recap of this week, but for the sake of completeness, I'll again write down the definitions. So the question here is, classify the following systems based on memory and causality. So what do you mean by a memoryless system? So a memoryless system, okay, before that, what is happening here is you have an input x of t that is passed through a system that applies it a function t and gives an output t of x of t. So a system is memoryless if t of x of t t of x of t depends only on x of t, or output, or let me write it in other way, a system is memoryless if current output depends only on current input. No past, no future dependence. And it is causal if current output depends on current and past input values. Okay, so now using this definition, let us figure out whether the given systems are memoryless and causal or not. So let us start with the first one. So the first one here is t of x of t, which is equal to t of xt. Now if you see here, this particular thing is output at time instant t, and here you have input at time instant t. So by observation you can see that there is no past or or and future dependency, which means that the system is memoryless. And since it doesn't have no future dependency, it doesn't have any future dependency, it is also causal, since no future dependency. So small takeaway here is, if a system is memoryless, which means it depends only on the current value of input, it is also a causal system. So a memoryless system is always causal. But this is not true, because causal can also take into account the past dependency, but memoryless does not, it doesn't even allow past dependency. So the first system input output relation is okay, so the first input output relation, whatever is given to you, is uh, memoryless and causal. So let me move on to the next question, next part of this question now. Someone is saying that I can't hear the voice. Am I not audible? Can someone?
You are audible only, ma'am.
Yeah, okay. Thank you. Thank you. Yeah. Yeah, there are some questions regarding the availability of notes and videos in the chat box. I'll answer them after the class, towards the end. Let me finish off this part. Okay. Okay, yeah. So let me move on to the second part of this question. So here t of x of n, this is a discrete time system, is given by summation k equal to n to infinity x of k. So if I expand this particular system, it is x of n plus x of n plus 1 plus x of n plus 2 and so on. So if I have n equal to 1, let's say, if n is equal to 1, then t of x of 1 is basically equal to x of 1 plus x of 2 plus x of 3 and so on. So all of these values from x of 2 are future values. Okay, so these are future values, which means that this particular system has a future dependence. which means that this is non-causal. Also, since it doesn't depend only on the current value of input, it is not memoryless. Or it is a system with memory. Is it clear? Okay. Let us look at the third part of this question then. So t of x of t is x of minus t plus x of t. Now to understand what happens, let's take few examples. Let us take t of x of, or let us say we have little t equal to 2. Then we have t of x of 2 that is equal to x of minus 2 plus x of 2. So this is the current value of input and this is the past value of input. So this is the past value of input. Okay, so by this example, at least we know that this is a system with memory. So this system has a memory. But is it causal? So for causality, we need to check if future dependence is not there for all values of t. So we checked for a positive value of t. Now let us check for a negative value of t. So let's say t is equal to minus 3. Then t of x of minus 3, it comes out to be equal to x of 3 plus x of minus 3. So now here, instead of past dependency, we now see a future dependency. So for negative values of t, the current value of output will depend on the future values of input, which means that for some t, there will be a future dependency. Hence, the system is non-causal. So therefore, this particular system, since it can either have past dependency or future dependency, it is neither causal nor memoryless. So this system is non-causal and with memory. Okay, any questions? If not, then I will move on to the last part of this question. So for the last part, t of x of t is equal to x of t plus x of t minus t naught, and I forgot to write this. This is for t greater than t naught. Okay. So if t is greater than t naught, so at t, this is the current input. And x of t minus t naught is the input t naught samples back, or t naught time instant back. So this is the input t naught time duration back, and that will be always a past input. So for all t naught greater than 0, x of t minus t naught is a past input. So the system has a past dependency. Since we have past dependency, the system is with memory. And since it doesn't depend on future values, since no future dependency, the system is causal. So this is an example of a system being causal but not memoryless. So the first example that we saw in this particular thing was a system that was memoryless as well as causal. So we said that every memoryless system is causal because it neither has a past dependency nor has a future dependency. But this particular system, the last one, it has a past dependency, therefore it is with memory, but it is a causal system because it doesn't depend on future values of input. Is it clear? Any questions till this point? So this was the last part I wanted to cover today. If you have any questions in today's session, feel free to ask. Let's go with technical questions first, then I'll move on to the other questions that are there in chat box. Any questions?
No, madam.
Okay.
No, ma'am.
Yeah. Okay, so someone is asking in the chat that can someone send recorded live classes? So this live classes will be recorded and uploaded on my YouTube channel. If you can access the chat box, I had already posted a link of the playlist in the very beginning of the class. So I'll just repost it. So maybe in 1 or 2 hours, I'll upload the video on the on my YouTube channel. You can access it. Another thing is the notes. The notes will be shared to you. So I have shared the drive folder link with the NPTEL people, but the updation of website is done by them. So whenever they do it, the notes will be available to you immediately. And once so basically you will get an Excel sheet in which you will find a link to a folder. And once that Excel sheet is made available to you, you can access the notes anytime. Another thing is, once you get that Excel sheet, after every class, I immediately upload the notes to that folder. So that won't be an issue. Only for this week, you wait for some time. They will take some time to update the link for all the courses. But yeah, it will be made available to you in a week or so. So yeah, notes will also be made available to you. This was the first session of this particular course tutorial. Every week for 12 consecutive weeks, like 11 more weeks, I will be taking a tutorial session that will cover the uh, that week's content and questions related to that. And there will also be a summary session that will be towards the end of this course, in which I will be taking a summary or recap of this entire course. And in case you have any questions, you can post it in the Q&A portal, and I'll take that particular questions also in that particular uh, summary session. The Excel sheet will be made available to you by NPTEL portal on the course web page, where you can access in the same left hand side panel, where you are able to access the links for the every week's lectures. At the bottom part, you will find feedback form and Excel sheet. I don't know if they have updated it, but they generally take a week's time to do that, but it will be available there. Any other questions? If you don't have any questions, feel free to leave the meeting. I will be here for a few more minutes. So if you have any questions, you can ask. Otherwise, you are free to leave the meeting. Thank you for attending today's session.